Welcome, everyone. Gurbir is our speaker today, and he's going to be talking about the Drinfeld-Sokolov reduction of admissible representations of affine Lie algebras. Feel free to start when you're ready.
Yeah, okay, thanks, Flor. So I think first I just want to thank all of you for the invitation to speak. It's really pretty exciting for me to get a chance to talk to sort of experts in vertex algebras. And so on that note, please do ask any questions or make any comments that come to mind during the talk. So, so in this talk, I basically want to share one theorem with you, and then maybe talk about some ingredients that go into proving it that might be new to you and hopefully might also be kind of interesting. And so the talk's going to be broken into sort of two big chunks. In the first part, after reviewing some preliminaries, I'm just going to state the theorem. And then towards the latter half of the talk, probably the latter third, I'm going to talk a little bit about some of the ingredients in the proof. So, so the talk is about Drinfeld-Sokolov reduction of admissible representations. So the first question is sort of representations of what? So we introduce some of the basic actors in the story. So let's write G for a simple Lie algebra. And let's also fix a level. So sort of you can either think of it as sort of some complex number in the standard way, or sort of the way I'm going to write it is I think of it as an adjoint invariant by linear form on the finite dimensional Lie algebra. So just some scalar multiple of the Killing form. And so to these two pieces of data, you can associate sort of the affine Lie algebra G hat kappa. And so what does that look like? So let me just remind you, you take just the loop algebra of your finite dimensional Lie algebra. So that's some infinite dimensional complex Lie algebra. And then sort of it turns out that most of its representations aren't quite representations of it, but you have to pass to one of these central extensions. Okay. And so, so this infinite dimensional Lie algebra, it kind of has a vertex algebra partner. So this is the vacuum Kac-Moody algebra. I'm going to denote it by sort of boldface V. And let me just remind you, sort of at the level of vector spaces, what it looks like is you take the parabolic induction from the finite dimensional Lie algebra to the affine Lie algebra of the trivial representation. And so the basic picture is sort of the trivial representation is generating some vacuum state, and then you take excitations. Sort of the first ones look like sort of just the copy of the finite dimensional Lie algebra times the vacuum. And when you take the OPEs for those fields, I mean, that's exactly your infinite dimensional affine Lie algebra, and then sort of everything else is just some normally ordered products of those. And so in particular, the point is that sort of the representation theory of the Lie algebra and the representation theory of the vertex algebra are exactly the same. So I'm just going to go back and forth throughout, sort of identify them. Okay, so so the Kac-Moody current algebras, they show up in, say, chiral conformal field theories with G symmetry. So let me just remind you, sort of in any sort of chiral conformal field theory, you always have sort of Virasoro symmetry. So I'm going to write sort of, again, sort of you have the Lie algebra version, you have the vertex algebra version, and again, it doesn't really matter which one, sort of the representation theories are the same. Okay, so the starting point for the theorem I want to talk about is there's this really nice correspondence between representations of the Virasoro algebra and representations of affine SL2. And so to the best of my knowledge, this was first kind of articulated in some work of the physicists Konizhnik, Polyakov, and Samologikov. And so in their writing, they kind of singled out that sort of the Virasoro representation they were most interested in were the ones showing up in minimal models. So these are sort of the minimal series Virasoro representations. And what they said should be the case is that you should be able to go from certain representations of affine SL2, the admissible ones, and you should be able to produce from them the minimal models Virasoro by you take the action of all these SL2 currents and you kill some of them or one of them. And so we'll say more precisely later what this gauging exactly is. But anyway, so that was their proposal, and then within a couple years, some other physicists, so Muki and Panda, they verified that there was this kind of correspondence, at least at the level of Q characters. And then the first people to kind of set this up mathematically were Fagan and Frenkel in 1990. So they rigorously did this gauging. So it was some BRST functor. So we're going to call it in this talk psi plus, or like the plus reduction. And so what it did was, its input was any representation of affine SL2, say at some level K, and its output was a representation of the Virasoro algebra, where the central charge depends quadratically on your level. But then an important point is that it really was only naturally a functor not between abelian categories of modules, but derived categories of modules. So throughout, when I say something like mod, I really mean an appropriate derived category of representation. And so let me just remind you of some basic properties of this plus reduction. So, it sent the vacuum algebra to the vacuum algebra. And a related nice property is that you build this functor using conformal field theory techniques. So it'll generally send any VOA with SL2 symmetry to another VOA. And then, so that's one comment, which kind of plays nicely with VOA structures. And another comment is that it plays nicely with highest weight representations. So the statement is that it sends Vermas to Vermas, and it sends simple highest weight modules to either a simple highest weight module or 0. Okay, and so part of the basic miracle here is that this functor, which when you feed in general representations, you get stuff concentrated in lots of different cohomological degrees. When you just only care about highest weight representations, you can just ignore all this derived category business and just everything lands again in the abelian category. Okay, so that's what Fagan and Frenkel showed, and in particular, when you restricted this functor to the admissible representations of affine SL2, it exactly recovered the thing that Knižník, Polyakov, and Zamolodchikov predicted. Okay, so now the point is, so that's the story for SL2, but the way that Fagan and Frenkel did this gauging construction, it made as much sense for any Lie algebra. So now the idea was that they could also produce a whole family of other VOAs, the W algebras, by a similar cohomological procedure. And this procedure not only gave you a way to build the W algebra, but it gave you a functor between the representation categories. And so again, the way you produce the VOA is you just feed in the vacuum algebra for Katz-Moody, you get out a VOA, and this is this principal affine W algebra. Okay. And so, obviously, I think a lot of people in this audience really like W algebras, and in this first paper, which kind of introduced them into math, it's really a fun paper to look at. But they articulated a conjecture, which was that this KPZ correspondence that worked so nicely for SL2 and Virasoro, that there should be some version of it for these general W algebras. And so let me formulate the most naive hope, which was roughly how they formulated it in their first paper. So the naive hope would be something like, again, Vermas go to Vermas, and say simples would go to maybe simple highest weight modules or 0. Okay, so that was roughly the state at which they left their prediction. But they said that Edward Frenkel, so one of the two, he had joint forthcoming work with Katz and Wakimoto that was kind of going to give a more careful analysis and a more careful prediction. And so that came 2 years later in this, this really nice, pretty famous work of Frenkel, Katz, Wakimoto. And so one of the basic things that they found was that when you go from SL2 to a general simple Lie algebra G, life gets a little more complicated. So here's the precise conjecture they made. So they said that when you feed in to this reduction procedure, again, one of these sort of the nicest Kac-Moody representations, one of these admissible highest weight modules, the prediction was that what you should get is either 0 or just sort of, again, an analog of a minimal model for the W algebra concentrated in a single degree. But the main subtlety was that it wouldn't always land in degree 0. So like they did a character analysis and they found like it's you get the character you want, but there's some funny sign. So they're saying that probably comes from like in the derived category, you're just shifting around your minimal series representation. And so I think the exact details of what the shift was and whatever, I mean, sort of the way I've wrote it here, it's kind of some qualitative statement, but they actually gave like extremely, like for every single admissible module, they give a prediction for like, does it die or not? And if it doesn't die, what's the minimal series representation you get and what cohomological degree does it land in? And the details of the prediction aren't super important for us right now, but let me just say that sort of the prediction, it really depends in a pretty involved way on the highest weight and on the level. So it's not, it takes some amount of time to sort of to even say what their guess was. Okay, so that was their conjecture for how to extend this KPZ thing to higher rank groups. But so another important thing that they did in that paper was they introduced another reduction functor, which they called the minus reduction. So it again took in Kac-Moody representations and gave you W representations. But sort of the way they constructed it, sort of their basic conjecture they made about it was that sort of it should behave sort of more similarly to the case of SL2. So namely that this minus reduction, when you feed in admissible representations, it'll again go to 0 or a minimal series W representation. But the key thing was that they did not think you should get any cohomological shifts. So basically for the minus reduction, you should be able to just ignore derived categories and just sort of work as naively as possible. So here's a rough summary of how they saw the difference between the plus reduction and the minus reduction. And I think that's kind of been borne out by history. So the minus reduction, I think definitely the advantage is sort of it behaves quite simply on sort of highest weight representations. So it's kind of, it's pretty easy to say which simples will die, which ones will live, and also sort of what the corresponding W representation should be. So that's clearly an advantage of the minus reduction. And so you might hope just like, oh, we can just ignore the plus reduction. It doesn't really matter. So unfortunately, some of the properties that we mentioned for SL2 of say this thing of like you send vertex algebras to vertex algebras. So those types of properties won't hold for the minus reduction. So for the plus reduction, sort of if you want nice things about compatibilities with fusion products or being able to relate things like conformal blocks and sort of in maybe sort of other modern parlance to summarize these kinds of structures, basically like for things of a global nature or things about sort of colliding different points and taking a fusion product, these types of factorization things, it's psi plus is going to play nicely with those in a way that psi minus won't. So it seemed to them that you kind of need to consider both. And as far as I know, that's still the case. Okay, so they made these conjectures in '92. as far as I understood, beyond the case of SL2, which Fagan and Frenkel had already proven at the time of the conjectures, they stood open for another, say, 15 or so years until, so there was some really nice work of Arakawa, and so he proved the Frenkel-Katz-Wakimoto conjecture for the minus reduction. Okay, and so so in his work, part of what he showed was that the same way that in the original work of Fagan and Frenkel, you could say something nice not just about admissible representations, but about all highest weight representations, you could say something very similar for the minus reduction in general. So among the things he showed was that this minus reduction is exact, so you can ignore derived categories. And again, it sends Vermas to Vermas, and it sends sort of simple highest weight modules to simple or zero. And so I want to emphasize it's exact only on sort of the category of highest weight representations. It's not going to be in general. And so the last thing I want to mention is that in those papers, he also got some partial results for the plus reduction. So namely, he was able to verify the cases of their conjecture where they expected no homological shifts. So in some sense, like in the cases where you could safely ignore derived categories, like he proved everything you would want to know, and it's, I think I'm preaching to the choir in some sense, but his work, it's like really, it's pretty beautiful and very influential. Okay, so the theorem I want to just mention today is that, so as far as I know, so after Arakawa's work, no more cases of the plus reduction conjecture were settled. But I guess, so in recent work, I showed that indeed, basically what they said, it's all true, and it's a nice thing. And so, in fact, the result I want to tell you about, it's not just something for the plus reduction, but for an admissible modules, but for sort of other reductions as well, and not just admissible modules. And so I want to tell you a little bit about what that more general statement is. And so to do that, I'm going to need to remind you about some things about Drinfeld-Sokolov reduction. But actually, maybe let me just stop here before I go and see, like, are there questions so far? Okay, great. So so for Drinfeld-Sokolov reduction, let me just approximate giving you the definition in steps by sort of warming up in some slightly easier cases. So, so the first thing is, so again, we're saying we need to gauge some action of some group. And so, the most naive way you can do that is when it's, say, not an infinite dimensional Lie algebra you're trying to gauge, but say a finite group. And so if you have a finite group acting on some representation V, say a complex representation, then so recall that you can make the invariant vectors and the co-invariant vectors. So that's like sort of, you try to gauge the action. So in the first case, you're sort of taking the maximal submodule on which the group acts trivially. And in the second case, you're sort of taking the maximal quotient on which the group acts trivially. Okay, so so a priori, there's sort of two different things you can do, but sort of a basic theorem, which is more or less equivalent to the complete reducibility of representations of finite groups, is that these two operations are canonically isomorphic. So the invariants and the co-invariants, sort of, you can identify them by some average. Okay, and so some sort of silly variation that will be important for us is sort of, if you also turn on a character, then you can make sense of sort of twisted co-invariants, where say now you take things which don't transform under the trivial representation, but say, this character, and even when you turn on the character, everything kind of just holds, just with a twist. Okay, so that's for a finite group. So as the next successive approximation, let's talk about gauging now a finite dimensional Lie algebra. So again, we consider the finite Lie algebra acting by infinitesimal automorphisms of some vector space. And we can just also throw in a character. So now this is homomorphism of Lie algebras from h to the complex numbers. So the basic new subtlety here from the previous case is that the functor of taking invariance or co-invariance, they're not T exact. And so sort of a priori what's at first the price to pay, which is that you need to consider the derived functors, turns out to actually be quite helpful in saying that the two things are really just the same operation. So let me just remind you what invariance looks like. So invariance or Lie algebra cohomology. So intuitively, you want to pass to the invariant vectors in M. So those are the things which are killed by the action of the Lie algebra. And so you make some sort of differential, which kind of looks like a de Rham differential that exactly checks whether your element is killed by your Lie algebra, and then sort of you can extend it to a whole kind of de Rham complex type thing. So that's the derived invariance. The derived co-invariance is something similar, where again, we need a quotient by some action. And so, you interpret the quotient as the zeroth cohomology in this complex, and you kind of keep on going to the left. Okay, and so the nice theorem here is that, again, the same way that for finite groups, a priori, there's two reasonable operations, but they turn out to be the same. So here you have these two operations, and they turn out to be the same. So the more precise statement is, so if you take your representation M, and you look at its co-invariance, what that turns out to be the same as is it's the invariance of not quite M, but a certain twist and shift of it. So you multiply M by the determinant of H shifted by 1. So it's some technical point, but the basic point is that, again, so for finite dimensional Lie algebras, there's only one way to gauge. Okay. And another way to say this, which will hopefully orient us for where we're going, is, in both cases, the complex that computes this stuff looks like M tensored with some exterior algebra. Sort of, when you write it this way, you start on one side of the exterior algebra and march to the other. When you write it this way, you start at the opposite end, sort of march back to where you started. And so if you sort of agree that they're sort of turn out to be the same, the symmetric thing to do would be sort of to start sort of halfway through the exterior algebra. And that's what it turns out is like the reasonable thing to do in the infinite dimensional case. So now if you have an infinite dimensional Lie algebra, so the technical thing here is a Tate Lie algebra, and you have a character of it. So again, so now you have your Lie algebra acting on some module, and you take some homomorphism from your Lie algebra to just the trivial one-dimensional Lie algebra. So again, the way you gauge the action is it's something called sort of invariants have some problems, co-invariants have some problems. It turns out if you take something which is halfway between them, all the problems kind of go away. So by problems, I mean, formally speaking, sort of commutation with direct sums, arbitrary direct sums. But anyway, so the point is that the complex that computes this sort of semi-invariance or semi-infinite cohomology, it just looks like the finite dimensional complex, but you kind of start halfway through. And there's some technical points which are that to say what halfway through is, you need to pick some compact open subspace. And similarly, there's sort of some anomaly you need to cancel to make it actually a complex. But anyways, the basic point is it kind of behaves like the finite dimensional case, and there's only one reasonable thing that behaves like the finite dimensional case. Okay, so this is exactly the type of procedure that goes into the definitions of this psi plus and psi minus. So let me just review for you sort of what inputs you put into this procedure. So recall we had our simple Lie algebra G. So we're going to fix a triangular decomposition, so into a so raising operators, a Cartan, and lowering operators. So we're going to fix generic characters of both the raising operators and the lowering operators. Okay, so psi plus and psi minus. I mean, sorry, I'm not going to be too careful about. Sometimes I'm going to write n plus, and sometimes I'm going to write n. Hopefully, that doesn't cause confusion. Okay, so the idea is that from these generic characters of these finite dimensional Lie algebras, we're going to sort of inflate them to produce characters of the infinite dimensional, so they're loop algebras. And so what do we do for the plus reduction? So for the plus reduction, we do the following thing. So if we take some element in this loop algebra, do you think about it as some sort of like, raising operators valued current on some formal disk? So what we can do is, so to get, say, not necessarily a number out of it, but say a power series, is you would just apply psi plus to E of t. So that would be now a Laurent series. So to make sort of a just number out of it, so we need some sort of canonical thing that goes from Laurent series to numbers, and sort of up to having the difference between Laurent series and sort of Laurent one forms. There's kind of only one reasonable option, which is you take the residue. Yeah. Okay. So the key point is that this residue operation, it's like some canonical like coordinate invariant thing you can do. And so that's roughly why this plus reduction is going to play nicely when you start trying to move on a curve. So for the minus reduction, you can do something entirely similar, where you just take the residue. But it turns out the thing that you want to do to make it play nicely with highest weight representations is you don't just do the entirely analogous thing, but you you just multiply it by a factor of t. And so this, on the one hand, makes you play nicely with highest weight representations. On the other hand, it breaks the factorizability of the function. And so anyway, so once you now have these two characters of loops into n and loops into n minus, now the plus reduction is you just gauge the raising operators with this twist, and the minus reduction is you sort of gauge the lowering operators with this twist. Okay, great. So let me just show you sort of what this looks like in the simplest case of SL2. So for SL2, you have sort of this business about lowering operators and a Cartan and raising operators. That's just the usual thing of F, H, and E generating SL2. And so let me tell you what this chi plus looks like. So again, it's something about a residue. So it's going to send E tensor T inverse to say a non-zero number. We can normalize it to be 1, doesn't really matter. And it's going to send every other monomial in E to 0. Okay, and so the key thing here is that it's doing something interesting to this one monomial in E. So the minus reduction, it's something kind of similar where, but again, now because there was this factor of T that was thrown in there, it's going to do something nice to F tensor 1 and send everything else to 0. Okay, so now again, the key thing is that the interesting thing is happening at this place. Okay, so a priori, you're gauging. So for respect to two different subalgebras of SL2 hat, and so I mean these are different operations, but the basic thing that you should notice when you look at this picture is that kind of the two things are kind of clearly related, which is that up to swapping E and F and possibly jiggling the powers of T, you're doing the exact same thing. Okay. And so how do you say this formally? So that gets us into something which is the spectrally flowed reduction functors. So passing between F and E, that's something about acting by the finite vowel group. So in that case, just the simple reflection in SL2. this thing about sort of jiggling which power of t your character is supported on, that's something about sort of acting by the co-weight lattice of the Cartan. So sort of that kind of controls sort of which powers of t your character will be supported. And so you can sort of put these two types of things together into something called the extended affine Weyl group. So it just looks like this finite Weyl group, semi-direct, this co-weight lattice. And then the point is that for any element in this extended affine Weyl group, you can conjugate, say, one of the two characters we considered, say this n minus chi minus thing, to get a bunch of characters of other subalgebras of G hat, and in particular, a bunch of reduction functors from G hat representations to W representations. And so I guess this has sort of two basic properties. So for one value of W, namely the identity element, you're not doing anything. So it's just a minus reduction. And then the thing we kind of said for SL2, you can do in general. So you need to switch between lowering operators and raising operators. So that's something about the longest element in the finite Weyl group. And then you need to sort of, slide up and down the powers of t a bit, and you have to put this co-character in. But anyways, the point is that sort of you can pass back and forth. Basically, you can put the minus reduction and the plus reduction into a whole family of functors. Okay. And so, by the way, so concretely in the SL2 case, it corresponds to saying like, oh, maybe I don't want this character to be supported here, but maybe on any other power. And similarly on any other power here, and asking what are all those reductions? Like what happens when you apply them? Okay, so now here's the statement of the main theorem. So it's going to apply not just to admissible representations, but any dominant simple highest weight representation. So here dominant means the following thing. So it just means that the Verma cover is projective in sort of category O. So it's kind of the top of a block. And sort of combinatorially, there's just some concrete thing about sort of it does not pair like a negative integer with any positive real affine cogroup. So that's what we're going to assume about the simple module we're feeding into these reduction functors. And then we're not going to make an assumption on the twist we take. So you can just take any of these spectrally flowed reductions. And then the theorem is the following. So it's you apply a spectrally flowed reduction to one of these dominant highest weight modules, and you either get 0 or a cohomological shift of just a simple W module, but in particular a dominant highest weight. So again, so for one value of W, this is Arakawa's theorem. For another value, it's the conjecture on the plus reduction, and basically it kind of you have a similar statement for everything in the family. Okay, so here are just a few comments about that. So first, to just get a sense of sort of dominant modules versus admissible modules, let's just look at an example. So if we take affine SL2 at say level 3/2, or if you're putting in the critical shift, it's -2 plus 3/2 if you work like naively. So in this case, so the highest weights for representations of affine SL2 at a fixed level, there's just like a line of them. I'm going to put some row shift in that, but let's ignore that. So there's some standard picture where sort of the affine Weyl group acts on this line by sort of affine reflections and translations and this kind of thing. And so I'm drawing here for you sort of the two walls corresponding to the simple reflections in the affine Weyl group. But anyway, so the point is that so in this whole line, which are colored red, you can ask, okay, which highest weights correspond to dominant modules? And the answer is you just have to puncture it at where I put these blue bubbles. So the exact details of where they are isn't super important, but just like you just have to throw away countably many points, or in higher rank, just countably many hyperpoints, affine hyperpoints. And so among all the remaining red points left on the line, you can ask where are the admissible representations. So at this level, there's 2 of them, which are just sort of right here between those 2 walls. And so the basic takeaway is just that, on the one hand, there are many more dominant irreducibles than there are admissible ones. But on the other hand, in some sense, sort of the most interesting ones are these admissible ones. So maybe the point of considering these general ones is just sort of to, in some sense, having the more general statement and knowing it should be true like helps you prove it. Because it's not going to be something about special properties of admissibles, but it's just going to be something softer about any dominant one. Okay, so then some other comments are, so again, I stated it in sort of a pretty qualitative way, but I mean, part of the theorem is, yeah, you can say exactly when the module either goes to 0 or doesn't. And when it doesn't, you can say there's a formula for like what the highest weight for the resulting W module is. And there's also a formula for what cohomological degree it shows up in. And so, so the formula, I can give it to you if you're interested, maybe afterwards, but the basic idea is, so it depends on your highest weight and your spectrally flowed reduction. And what it is that from this data, you get this determines for you some element in some other Coxeter group, the integral vowel group of lambda. And it's the length of that element. That gives you the cohomological shift. And so there's a comment to make here, which is that this actually corrects the Frankel-Katz-Wakimoto conjecture. So in their conjecture, they had something about semi-infinite lengths, but it's just the usual length. And then a final comment is, so the way we said it was you fix a dominant highest weight module and you take all these reduction functors. But there's another way you can phrase this, which is equivalently what you're doing is you're taking just either the minus reduction or the plus reduction, and you're applying it to sort of a family of not highest weight modules, but just simple Kac-Moody representations, which are you take your simple module and you start just conjugating it by elements in the loop group to get other representations. So this is some version of, say, for finite dimensional SL2, if you conjugate, say, a highest weight representation by the simple reflection, you'll get like a lowest weight representation. So it's that kind of thing. Okay. So I guess in the remaining time, I want to talk a little bit about some of the things which go into it, which might be fun or interesting, but maybe actually let me stop again to see if there are questions.
Can you just explain again what the dominant weight was?
Sure. So the statement is, so how to say it? So, like it's, so in the same way that sort of like an anti-dominant weight, sort of, you can either give a combinatorial criterion for what that means, but representation theoretically, it's just saying that the simple module is the same as the Verma module.
Got it.
So, and the point is that, so those are they're kind of bottoms of blocks, roughly. So the idea is that sort of dominant just means sort of the top of a block, and sort of, so then again, it's sort of combinatorially, it's something that you're never on the negative side of one of the co-root hyperplanes. I mean, and just really some integrality thing, but morally, it's like you're never on the negative side. And then sort of non-combinatorially, it's saying that the Verma module, it's not the same as the simple, but rather it's projective.
Got it.
That's all. Yeah. Yeah, thanks for the question. Okay. And by the way, I should say, so all admissibles are dominant. So yeah, this is a, yeah. Okay. So maybe let me go on to say,
I have a question, sorry, Gurbir. I'm not sure if it makes sense, but so you said basically you have like 5 plus and then 5 minus as two maybe concrete cases of a more general thing happening, right?
Yeah.
Can you control which ones are good, like with fusion or with BOAs? Do you see it in any way in your formulas?
This is a great point. So I think the statement is that I would love to be wrong about this, but I think only a finite vowel group's worth are going to play nicely with fusion, because roughly it's only like of all the choices of chord, like there's only the residue. That's like the only canonical thing. So you could take the, you could do it for n or like n minus, but like you really should do the residue to get something factorizable. But yeah.
Thanks.
Yeah, sure. That's a good question. Okay. So in terms of the ingredients of the proof, I'm going to say some stuff, and hopefully I'll say it in a way that you can get the gist. But the main takeaway is just the following thing, which is, so we said that we put the plus reduction and the minus reduction into a family of functors, the spectrally flowed reductions. And I think a point which might not be obvious unless you're thinking about it from a certain perspective is that sort of these functors, they naturally sort of fit into sort of appropriate, like in some sense, they generate some nice category of functors. So like basically it's there's certain ways in which these spectrally flowed reductions talk to one another that sort of, when you sort of put them all together, you get some nice functor category. And in particular, the usefulness of that is that once you know sort of a place in which they all live, that helps you start proving identities relating different ones. Okay. So this is slightly vague, but I'm going to try to say it more precisely. So the tool that lets you do this is something called categorical representation theory. And so the basic idea here is pretty simple, which is that sort of in normal life, sort of you're used to having groups acting on vector spaces. And the idea is that there's a nice and useful similar theory where you have groups acting not on vector spaces, but on categories. And so there are a lot of people whose ideas have gone into this. So some names here are sort of Bailenson and Drinfeld, then Frankel and Gates-Gorey, and then there have been later contributions by Bensby and Nadler, and then Dario Beraldo and Sam Raskin, and the list goes on. And so just some context for like what part of the world this stuff comes from. So it really came out of geometric representation theory, and kind of it plays a big role in sort of the modern formulation of sort of local geometric Langlands or local quantum geometric Langlands. But so here's the basic idea. So so I'm writing on the left-hand side sort of things from usual representation theory that you hopefully know and like, and I'm just going to say like roughly there's a similar thing in the categorical thing. So okay, so let's just consider a finite group on the left-hand side, and sort of the analog is we're going to need some notion of sort of when points are close together or far apart. So more precisely, we're going to work with an algebraic group H. So the analog of a vector space being acted on, so I said before, it's a category C. Now, there's some technical point here, which is that what you typically work with is, it's not a category, but a DG category. And the technical assumption is normally you want to work with co-complete DG categories. But you can just read this all as a category. Okay, and so and in normal representation theory, sort of in action of a group on a vector space, so it's for each point of the group you get some automorphism of it, but then you can also take linear combinations of those, and that gives you a module for the group algebra. And so so the group algebra, that's just functions on H, and that kind of has some convolution product. In particular, sort of indicator functions correspond to the original elements of the group acting. So in the categorical setting, you have some version of the group algebra. I'm going to put that in quotation marks. So what it is you take the category of D modules on H. And so that's the thing which is going to act. And so naively, the way you think about this is, so each element of your group is going to act by some automorphism of your category. And that's going to correspond to now, instead of indicator functions, things called delta functions, delta function D modules on your group. And now the key thing is that basically you can also take these like nice sort of continuous linear combinations of those symmetries to have not just these delta functions act, but sort of any D module in H act. Okay. So just think of that as something like the group algebra. And so normally you can talk about invariance or co-invariance, and you can do the same thing here. So given a subgroup K and H, you can talk about the K invariant vectors, or similarly here, you can talk about the K invariant objects. So that's just an operation which makes sense. And similarly, sort of, you can twist by a character in the finite dimensional, so I mean, in the case of the finite group, and sort of, you can also sort of consider sort of twists or like the simplest representations. And so these are sort of, the twist is not by a character, but by something called a character sheaf. And you can again form these twisted invariants. And so the following point is kind of the key one. So please ask questions if what I'm about to say is not totally clear. So there's a very nice thing you can do in the case of the finite group, which is the following. So it's, if you start with invariants for one subgroup in your vector space, there's a natural class of operators that take you to invariants for another subgroup. So namely, if you want to go from like the K1 invariants to the K2 invariants, you can just multiply by things in the group algebra that say are K2 invariant on the other side, and I'll tell you you land in the K2 invariants. And then it turns out there'll be some redundancy in the convolution on the other side, so you can mod out by K1 to accommodate. But so the whole point is that you can pass between invariants for different subgroups by convolving with functions on a double coset. Okay. And so the analogous thing here is there's just like, you can write down the exact same formula, but now it's sort of some convolution algebra of D modules instead of functions. Okay, great. So again, when you look at these types of formulas, you just always think like, oh, what's the function theoretic analog? And you kind of understand. Okay, so how does this all fit into the stuff we were talking about earlier? So the key point is that an example of one of these categorical actions is, the category is the one we've been interested in all along, which is Kac-Moody representations, and the thing acting on it is the loop group. And so we kind of said that, again, you think of a categorical action intuitively, it's like each element of your group is acting by an automorphism, and then there's like this non-trivial statement that you can take these kind of big linear combinations. And so let me just tell you what just the action of just the group itself is on this category. And that's just the following pretty simple thing, which we already kind of said, which is that if you have any element in the group, just conjugating by it gives you some automorphism of the Lie algebra. So you can sort of move around representations by sort of just, changing the action by this automorphism. And again, this is the kind of thing where you switch highest weight representations to lowest weight representations, this kind of thing. Okay, so the claim is that sort of that action, it kind of extends to like one of these sort of categorical actions in the previous sense. Okay, and so in the thing we were studying, we were kind of trying to understand like what happens when you take something in category O and you apply one of these Drinfeld-Sokolov reduction functors to it. So we were going from category O to representations of the W algebra. And so the nice thing is that both of these categories have nice descriptions in terms of this kind of categorical representation theory stuff. So to state this, so recall that category O, it's something about sort of, something like a Borel is acting sort of locally finitely on your representation, yeah? And so it turns out, so the thing which is the analog of the Borel is this Iwahori subgroup. But the key point is that what category O is in this language is it's the category of I invariant objects in all of Kac-Moody representations. So the idea is that like I invariants, or in general for like a group, a subgroup, passing to I invariants in the category of representations, it's passing from all representations to the corresponding Harish-Chandra modules. So you take things which are integrable for that subgroup. Okay, and so so that's kind of category O. And the idea is that for W representations, you can do something similar. So this residue character thing we talked about for the Lie algebra, it kind of exponentiates to some sort of residue character thing for the whole group of loops into N. And So there's a nice theorem of Sam Raskin, which tells you that sort of the Whittaker invariant objects in Kac-Moody representations, that's just the representations of the W algebra. Okay. So again, so the point is just that sort of, at the very least, as some organizing principle, you can start using these sort of function theoretic analogies to understand the objects that we're playing with. But then the nice thing is that, so now again, so we said before that if you take things which are invariant for one subgroup and things which are invariant for another subgroup, you can kind of go between them by convolving with things supported on double cosets. And so the nice thing here is that when you look at this relevant, category of D modules on some double coset space, these spectrally flowed reduction functors, sort of in some precise sense, they generate this whole category. And the other nice thing is that sort of each spectrally flowed reduction functor has a really simple geometric description. So it corresponds to something like an indicator function on a single double coset. And so the basic idea is that now once you've put these spectrally flowed reductions into this family, and you have this nice geometric picture for what they are, you can kind of study them geometrically, in particular prove identities between them geometrically. And so that's, in some sense, that's the basic extra thing that lets you, say, prove these statements for the plus reduction, knowing, say, the statements from the minus reduction. So you prove identities relating the two functors, and then you sort of analyze what those identities tell you about where things go. Okay, so I think, let me just say something pretty briefly, which is explaining how this previous thing I just said about the spectral flowed reductions kind of fitting into this nice family, what it has to do with, say, something that you might like and be familiar with already, which is this Arakawa-Fagan-Frenkel duality for W algebras. So let me just recall that sort of the W algebra you build from G and kappa, it kind of has a Langlands dual description where sort of you can build it using the Langlands dual Lie algebra and sort of some Langlands dual level kappa check. And so, so Gates-Gorey conjectured in 2007 that this kind of functor category that we were talking about that contains the spectrally flowed reductions, so that category for G is just the category O for G check. Okay, so there's something funny where, like, on the functor category in one description, on the Langlands dual side is the category of highest weight representations. And so this conjecture, we proved it last year with Justin Campbell and Sam Raskin. And so Gates-Gorey also conjectured the following thing, which is that, so you take, so just ignore Langlands duality for a second. So just on either side, you can take, a spectrally flowed reduction and a representation, you can pair them to get a W algebra module. Or you can do the same thing on the other side. On the other hand, you know that those two W algebras are the same. And so you can ask if the following diagram commutes. So you start with a spectrally flowed reduction and a highest weight representation. You turn the spectrally flowed reduction for G into a highest rate representation for G check. You turn the representation for G into a spectrally flowed reduction for G check, and then you do that pairing on the other side. And the claim is that the answers you should get should always be the same. And so some cases of this conjecture were settled by Arakawa and Frenkel in 2019, and that's exactly this Arakawa-Fagan-Frenkel duality. And just the last thing I want to say is that I think the general case, I think I know how to do it, so hopefully I'll write it up at some point. But again, the main thing was just that these functor categories, they already show up in things that hopefully you already know and like, which is sort of these identities relating reductions and Fagan-Frenkel duality. Okay, that's all I had. Thanks very much for listening.
Thank you so much. Thank you so much, Gurbir. Let me stop the recording so that everyone feels free to